Today we're going to be looking at VERICUT's force optimization. Force is physics-based optimization that recalculates feed rates and subdivides motions in order to maintain a constant ideal chip thickness for machining as much as possible. And simultaneously, when needed, it will reduce feed rates in order to avoid excessive cutting forces and spindle loads. Let's take a look at the part we'll be machining today. This is a titanium piece of material. We can see the part inside, so we can see what we'll be creating. It has very typical aerospace geometry with pockets and ramping walls, periphery, and so on. And as I mentioned, it's a titanium part, so not the easiest to machine. To focus on the machining, we'll use VERICUT's workpiece view. VERICUT Force needs three things in order to be successful for you. First, it needs you to verify that the part you're machining has a good clean NC program with no mistakes or errors. We've already done that in this VERICUT session. Second, it needs intelligence about the machining tools and what they're capable of machining. So if we look at VERICUT's tool library, we'll notice it has stock material records, and these records are defined for use in titanium metal. You can have any number of stock material records under any cutter, and each one is unique to that cutter. So you can have roughing versus finishing, and of course different shape end mills as well. I'll show you a little bit more about these later. The third thing VERICUT needs is it needs to know what type of material it is you're actually cutting. You do this in VERICUT's Optimize control window. When we go to optimize the NC program, since we're using force technology, we'll go to the force material catalog, and we'll want to search for the titanium material that we're looking to machine. As we key in the filter, VERICUT filters down the list to show us various grades of titanium. You can also use alias names for material. So if titanium isn't a name that's familiar for you, and maybe you're familiar with something like TC4, you can filter in by that name as well, or by these ISO code groups, whichever is easiest. When you see the material that you want, you can right-click on it and send it to the Optimize control window, and boom, it ends up over here. You also have that same option at the bottom of the window. We're now ready to optimize. Here's the NC program that VERICUT will be simulating. As you can see by the notes inside, this program contains adaptive milling motion, which is cam optimized NC motion. We'll be seeing what force can do with that. As we start the simulation, optimizing is taking place, and we'll be able to see what VERICUT does with this motion as far as feed rates and machine time. Up in the upper left corner, I have the head-up display configured to show us the program feed rate, which you can see is rather motionless, and the optimized feed rate, which you can see there's a tremendous amount of activity going on over here. These are the different feed rates that Force is calculating for us and outputting to a new optimized NC program. The machine time, and then the optimized machine time, where you can see the difference. Down in the lower right corner, I'm using the tool use graphs to show the difference between the original NC program and the optimized NC program. Wow, it's finished already. So let's take a look at those results. These are all of the tools that ran. We can look at them one at a time and compare the original time versus the optimized run time, or look at the entire operation. In the part savings area, we see the amount of time it took to machine the part with the original program and then the optimized program and percent savings. Nearly 20% savings on a program, remind you, that was an optimized type of a program out of a high-end CAM system. That's quite a bit, but normally you'll see more. If you optimize just an average NC program that you have in your shop, you typically will see 25 to 45% savings, even in hard metal parts like titanium. Now this calculator window is designed so that you can put in data about your machines in your shop and get an idea of the savings. This example shows 100 parts being run. We can change the shop rate depending on what our machines cost for our customers, and then hit the calculate button to get the savings for that part run. To get a better view, you can extrapolate that over your entire operation of shifts. So here we have 5 NC machines running parts like this, cutting titanium metal, for example, and if we optimized all those parts, those machines ran at 8-hour shifts, and this shop has 2 shifts running. Here's your number of average work days, and just calculate the yearly savings. 350,000 plus on this particular type of a part. As you can see, force optimization will pay for itself normally in less than a month. Now we'll take a look at those graphs that I shoved to the side a few minutes ago. These graphs contain a wealth of information about the machining process. You can see there's tons of data metrics that we can take a look at in graph form. I'm just going to use chip thickness and total force and give you some ideas how these graphs work for you and information that they can show. The graphs are interactive with the part and also with the NC program. So for that, we'll use the docked view of the NC program, and we'll put the part over here just where we can keep an eye on it. For starters, let's take a look at the first tool. Now I've got a couple of different graph lines going on here and some colors, so let me show them to you one at a time. This is the original NC program graphing that we can see for this first cutter, and the cut color that you see in the background ties to the color on the part to give you a clue of which machining operation or toolpath you're examining. Now looking at the graph activity, we see that it looks relatively constant, but you've got this red dash line up here, which is the target chip thickness for this operation and this tool. So what the graph tells me here is that we're beneath that line by a significant amount, which tells me that the tool has not been programmed efficiently. There is one lonely spike right here which kind of puts us in and around where that tool could perform, but the rest of it is performing to a substandard level, inefficient. We would like our optimization to fix that. So if we look at the optimized NC program, it looks quite a bit different. You'll notice there are no inefficiencies. All of the cutting engaged with material is occurring right at the ideal chip thickness for that tool. That's what you want to see. Now look at the cutting forces. They're still below the ideal cutting force of what this tool can withstand. So there are no problems with cutting force. Comparing the two, we're actually able to see with the dark green where the NC program was running, and with the bright green shows you what was raised in order to get the chip thickness where it needed to be. And you can also see the difference in force that was applied by increasing those feed rates in that area, none of which threatens the horizontal line for total force. Let's look at another tool. This particular tool demonstrates something else that force is unique about handling for you, and that's making corrections to the NC program when things are looking too aggressive. Anything above the red line, like all of these spikes in this area here, are excessive tool forces or excessive chip thickness, which caused these tool forces. Let's take a closer look. Again, the original NC program shows these force spikes, and you'll notice out on a real part in the shop floor there'll be chatter marks. This could be where a tool had trouble and an operator had to dial the machine back with his override, or maybe even the tool got damaged with broken teeth or snapped off. These are all things that can happen with too much tool force. In those areas, in order to keep the forces in check, what force optimization had to do was reduce the chip thickness below what the ideal amount should have been, but it had to do so in order to save the tool. This is the saving measure that VERICUT Force is unique in having to present the best tool life and give the tool spindle a break and not have any problems. So it keeps a constant running tool force in those areas, and you could actually hear that on the machine. So this actually is what improves your tool life. There's one more thing I want to show you about the graphs while we're here. VERICUT has a NC program review mode, which is linked to the graphs that allow you to go back and review any of these conditions that you are concerned about. So let's go back and look at the original NC program once again. And this time I will click in the graphs in order to have VERICUT put the material back to the state that it was in right at that time it was processing that motion. So here's the cut, and I can use my thumb roller here to go backwards and forwards in the graphs. So as the cut began, you can see it's right on the profile of the wall, a relatively light cut, and going forward it gets into the corner. Still looks pretty good. You can see where the cursor is on the graphs here, the blue cursor. One more time, and then right here where it hits the wall at 90-degree angle, it opens up a cut around the face of the cutter, which is where all of the chip thickness was increased, and so were the cutting forces. And that's usually going to present itself as chatter marks in the corner. Some programs have a slow down feed rate for corners. This one obviously didn't. So what did Force do with that? That's where it had to reduce the feed rate. So it gives you automatic corner slowdown to make sure your corners come out nice and dimensionally correct. And then it will take off and go into the next corner and do the same thing again. So a very nice way of using VERICUT to be able to go in and analyze the tool motion and investigate problems to learn what's causing them. So some people that use our force analysis software will use the software just for that and be able to analyze the cutting forces at play in VERICUT. But if you want to fix everything automatically as well as optimize, you would use the force optimization software, which also comes with analysis. So we'll close the graphs for now. And maybe the next thing we want to do is take a look at what does the optimized program actually look like. You can do this through the Optimize tab and comparing the files. The file on the left is the original NC program. The file on the right, the output optimized NC program, as evidenced by this banner at the top of the file. So what I want to point out for you is here is the original NC program feed rate for the very first operation of the very first tool, 29 inches a minute. In the optimized side of things, we see that as well, but then the tool was in error, so it was increased automatically by force optimization to 750 inches a minute while the tool's moving in air and not removing any material, and then slows down prior to engaging material. But after that, look what happens with all of the feed rate scheduling that goes on and block breakup. This is the amount of subdivision that causes very precise, constant chip thickness at the ideal thickness you want for machining this material. Nothing like the program that came out of the CAM system. So that's what's causing all of the savings. Some people think that by having all of this feed rate activity that causes some erratic machine behavior. But in fact, what's going on is it's causing the machine spindle and the spindle load to run much more evenly than the original NC program. So the benefit to the machine is significant, as well as the benefit to the tool life, keeping that constant chip thickness right where it needs to be for machining. We have our Force users reporting from 2 to 3 times tool life what they get with Force optimized programs.